Okay, we're going to look at doing a state machine driver for our rotary encoder. And basically let's review the A and B outputs of our rotary encoder. Generally you start off in your detemp position. It's usually both A and B are pulled high. To go in the clockwise direction, this sequence is followed going up this table. And that's from 3 to 1 to 0 to 2. And then it starts over. And counterclockwise goes from 3 to 2 to 0 to 1. And then it starts over. And so that's our outputs basically that we're going to use. And we'll just use these outputs directly for our states in our state machine. So let's see how this works out. First we're going to start off at our detemp position. So here's our first state. This is the A pin, this is the B pin. And now let's first draw the counterclockwise direction. So we'll be reading down this list here. So we'll go from state 3 to state 2. The next state, we go from 2 to 0. Now from state 0, we go to state 1 in the counterclockwise direction. And from state 1 in the counterclockwise direction, we go back to state 3. Now let's do the clockwise direction. We go from state 3 to state 1. And I'll draw that on the diagram in the clockwise direction just so we kind of helps us keep straight. So we're going from 3 to 1. Now from 1 we go to 0. And then from 0 we go to 2. And at 2 we wrap around back to state 3. Now you can see a problem right away with this. We've got 2, 4, 6, 7 states, and we've got 3 duplicate pairs of numbers. Well, that doesn't work for a state machine. We want to differentiate the clockwise loop, and we want to differentiate the counterclockwise loop. So we arbitrarily just stick in another bit, and we make our states unique. We'll just arbitrarily choose for counterclockwise. We'll add a third bit, and we'll make that bit a 1. Okay, now our counterclockwise bits have states of 6, 4, and 5. And now we'll add 0. So now we have 7 unique numbers. That's pretty cool. One thing that's missing, we can represent 8 states. So we have a number missing, and that's state 7. And you should always account for all your states in a state machine just in case. So state 7, I don't know how we'll get there, but some kind of a problem, a bit error or noise, something like that. If we ever end up in state 7, we'll go to the start just arbitrarily whether we're there or not. At least we'll get into the state machine operation proper and recover from this state. It might cause a temporary error, but it's better than being totally lost. Okay, we've got our state diagram shown for going smoothly in one direction or the other. Now it's possible due to noise or the actual movement of the rotary encoder to get, like, go to this state, and then go back. So those are possible transitions. So let me just show all those. So now the green arrows are the normal direction for clockwise and counterclockwise, and the blue arrows are the backing up from the normal direction you're going. So we see that from state 1 you would most likely go to state 0, which would be the clockwise rotation, but you can have a counterclockwise rotation, and you'd want to go back to your starting state. and the same for every other state. It has a backup direction and a forward direction, and this one backs up to 2 will back up to 0, or 2 will go forward to 3, the starting position. Now we want to indicate when we make a complete revolution and get back to our detent position, or state 3. So going counterclockwise direction, we want to indicate on this move that we've made a complete rotation, or not a complete rotation. We made a complete step in our whatever our percentage of rotation is. So in this transition, we want to set some kind of flag. The details aren't important right now. Some kind of indication that we've gone through this path counterclockwise. And the same thing for the clockwise rotation. When we make this transition from 2 to 3, we want to set a flag or something that tells us we've completed the cycle in the clockwise direction. Now the thing that keeps the state machine from messing up is when you're in your home state. Say we got there by proceeding from state 2, indicated a clockwise increment, and we went to state 3. Now due to noise, 2 again. If we just go back to state 2 due to noise, and then the noise goes away and we go back to state 3, we'll indicate another clockwise rotation. But that didn't happen at all. We don't want to, due to noise, go back to this state or back to this state, because the noise goes away, we'll go back here and we'll re-indicate that we made a rotation when we didn't in fact make a rotation. And if the B channel goes from changes from 1 to 0, we want to make sure we go to this state, like we're going counterclockwise, and not go to this state. And the opposite is true if the A pin has noise on it and it goes from 1 to 0, which would be these 2 states. This is our complete rotation. If we get that noise on channel A, we want to make sure we go to this state, because this starts a new rotation. We won't go here and back and forth here, falsely generating this flag for counterclockwise. So we want to make sure our state table, there's no path from this direction from 3 to 5, and we want to make sure there's no path from 3 to 2. So let's go ahead and look at our code and see how we might implement this in the software. Okay, here's our sketch, which controls our state machine driver for the rotary encoders. Basically, I've taken this code from this page right here, and this guy implemented a state machine method that closely follows what I've described on the whiteboard. Now, he had it written as a library. I basically changed it where it's just a self-contained sketch, so you don't have to worry about other libraries. I had some references I never could fix, and this is just a basic sketch. And the only thing you need for it is MS Timer 2 library, which you can load off Arduino.cc. So we've got basically 2 different methods of interrupts that we're going to test out here with our state machine. The first one is called the Timer 2 interrupt. It just generates a periodic interrupt using Timer 2 as a time base, and basically it's interrupt polling of the rotary encoder. The other method is the pin change interrupt, and this is where both pins A and B that are connected to your Arduino board, your Uno board, or whatever it is. Any change causes an interrupt. This only runs, there's only an interrupt when there's actual activity on the rotary encoder. Now you can only define one of these at a time, otherwise they'll conflict. I'm not sure what would happen if you define both of them. And there's also the ability to enable pull-ups. If you need pull-ups, you don't have pull-ups on your encoder and you want to use the ones on your Uno board or whatever, you can define this value. The encoder I've got has pull-ups located on it, so I don't use it. Here's your load MS timer 2 interrupt. This interrupt times in milliseconds, and I have it configured to time in 1 millisecond, which is the slowest speed right here. Interrupt polling. So 1 millisecond, I believe, is the fastest it can go, and that should be fast enough. But that's 1 millisecond running continuously. Here's the definition of the state table. Now the original definition is up here. I have commented out, and I commented it out because he defined 0 as start, or the but you know, detent, usually detent A and B are both high, so that's about all I've changed, is just rewritten the table where start is 3, 0, 1, 2, 3, and went and made some small modifications from there. Otherwise it's the same thing. I also added the illegal state 7, so if you get in state 7, it'll go to start no matter what. That's basically the only change to that. The way it works, you just do your setup. If timer 2 interrupt is defined, it sets that up. If the pin change interrupt is defined, it sets that up. Print your prompt. And the interrupts right here are both identical. The content is both identical. This is the pin change. Like I say, only runs when there is actual pin change. And timer 2 interrupt runs continuously at whatever rate you decide to run it at. And the loop, all the loop does is look at the old count and compare it to the current count. If it's different, it prints it and updates the old count value. It just sits there and does that. The interrupt routines, both of them count, increment or decrement the count. So that's all there is to the interrupts that we're using with our state machine. Right, so let's check out how the code works on our rotary encoder. I've got the same hardware setup I had in the previous video. It's got the Whiteboard, and it has the really noisy rotary encoder installed. So this is about the worst case test I can give this thing. So I've got the code loaded that has the timer 2 interrupt, just the interrupt polling that discussed in the code review. So let's see how that works. I gave it just a regular 1 revolution, and I went one too far. And we're at 20, so that works good. Go past 0, go negative, 2 revolutions counterclockwise, and negative 20, so that's good. So we'll put it back to 0 just for grins, and I'll give it a high speed turn. Well, I'm not sure if I went twice or not. Went too fast. Restart at 0, try it again. Oh, and I missed about half of them. So Now go counterclockwise. That's 2 revolutions. Missed about 11 of them. So you can make this miss with the interrupt polling. Now you can increase your poll rate, but that, you know, takes more time away from the rest of your application. Of course, the application here is only doing this, but if you have something that's time critical, you're going to need to worry about how much time you're spending in your interrupt routine. So, okay, the next test I want to do on this is that little partial turn counterclockwise or clockwise to the indent. It's where you turn it but don't quite go to the all the way to the indent, and you come back to the original indent. So let me try that. I'm doing clockwise. Well, that actually went too far. It's not doing it. Try counterclockwise. No, it doesn't affect it. You remember in the first video we had some backwards counting and forward counting when you did this test, but the state machine has taken care of this situation now. It can track partial wave in any direction, and also recover if you come back and don't go all the way to an indent. So it looks like the state machine has fixed that problem really solidly. Well, that shows that the polled interrupts do have an issue for high speed turning. And so let's see if our so let's see if the pin change interrupts help any. Let me set up for that. Okay, now I've redefined pin change interrupt, defined that, and have not defined timer 2 interrupt in the code and download it. So we're ready to go with this guy. Do a normal clockwise turn for 20. And go back to 0 and further counterclockwise to -20. That's working good. Just for the heck of it, I'll spin around back to 0. Now I'll go as fast as I can. We're straight up and we're at 20. Go counterclockwise a couple times. Right on 20, -20. So it seems like $40, that's straight up and down. Multiple of 20, 40. This is going to be very hard to break. This is tough to break. I don't think it can be done. Well, it probably can be done. I have done it, actually I did do it one time in testing, but it's really hard to hit. You have to go really, really fast. Faster than your interrupt service routine is to beat this. So, and let's try the, go back to 0. Let's try the partial turn clockwise. Of course, the state machine has taken care of this. Whoops, I went too far. Went too far again. Yeah, I don't see any. Go counterclockwise, partial turn counterclockwise. It's just not the state machine's handling. Of course, it doesn't matter the interrupt here. It's the state machine that's taking care of this problem. So our partial turn problem is solved, and it looks like speed and noise are solved by the state machine with the especially in the pin change interrupt. So So that's pretty much all the testing. As far as this, we're going to do, last thing we're going to do is look at velocity testing. Alright, here's the code to do our velocity detection. Basically it's the same thing as the other previous code. The only difference is you have to use MS Timer 2. That's our time base to measure activity, how fast the activity is on the rotary encoder. This is only uses to run the actual rotary encoder. You have to use interrupt, the pin change interrupt. So there's no option for that. You need both those interrupts. There's a few more variables to track while we're tracking velocity. Here's our same state machine as we used in the previous code. Setup, that's going to be pretty self-explanatory. Your setup time here for how fast the interrupts. I've slowed this down. This will affect your counts. This is a value you can play with to adjust how the program responds to your rate of change on your rotary encoder. That's just one of the variables. Everything else is pretty much the same. Here's the pin change interrupt. It's just the same code as in the other previous code. It does exactly the same thing. Okay, here's the timer 2 interrupt. It starts out by seeing if you're turning the dial, and it waits until you stop turning the dial. And then when it stops turning, it starts incrementing this pause detect variable, and that'll wait for a period of time depending on what the number of counts you give it and how fast your your timer 2 is running, how fast your interrupts come. That all determines how long this takes. But eventually you count up, you've realized your knob's not turning anymore, so you can go ahead and do your calculation. And what it does is just see how many counts there are in that period, and is it greater than a value called speed. And of course you can play with the speed value and get the response you like. The way it's set up now, you have to turn it pretty fast to get the change. When you do get the change, you add a value or subtract a value called velocity, and that's how the big jump you make. Now it should probably be some multiple of your clicks per rotation, but it's up to you exactly what it is. I have it like, I think I've got it at something like 150 or 100, which is a multiple of 20 revolutions, which is the current encoder I'm using. So you can play with velocity, speed, and the timer value you set up for these interrupts will all have an effect on how it responds to your rate of change. The idle limit here, that's how long you wait till you've stopped turning the knob, and this is probably not very sensitive to much, but it's something you can play with. It doesn't really affect the velocity directly, but it does affect knob response a little bit. So basically those values are what you want to play with. Then in the loop's the same as the other loop. You just prints out the count as it sees it change. And so we're going to take a look and see how this behaves on the breadboard. So here's the velocity test. We're turn the knob at high speed and it should count up. Now this is just the pin change interrupt, and the timer 2 interrupt is handling the time base to measure our speed with, as I described in the software. So let's see if it counts normal. Going normal up to 20 and we're zeroed. Now see there, now I turn fast. Let's go back and take a look. Here it was at 26, went to 126, and then started counting up normally. And it looks like I also hit, I kept up the speed for long enough and went from 133 to 233. So it looks like our velocity is working. Let's try, oh, I should have, sorry I didn't measure that we were still in sync. Re-zero my knob, get a reset, count up some, go fast. It's 132, go up straight. That's 140, we're still in multiples of 20. Haven't lost a count. We're right on our rotations. Now go backwards, go negative some, and speed up. And there we have, there we go from 38 here to 138. And from 144 to 244. And back to 0 and a multiple of 20 ticks per rotation at 240, and we're good. We haven't lost a count. So it looks like velocity is working. The way how it responds is totally up to how I set up the parameters in the code. So you can play with that to get different responses to velocity. So okay, well, thanks for watching. That's all I'm going to do on rotary encoders right now. Might end up putting them on the putting 3 of them on the serial LED display and play with some colors that way. Otherwise, thanks for watching. Take it easy. We'll see you later.